Hello friends and a very warm welcome to C4U. This video is about Claisen rearrangement, its mechanism, and we are going to solve some problems, of course. So basically the Claisen rearrangement is nothing but the intramolecular rearrangement. Intramolecular means it occurs within the single molecule, within a single molecule, and it occurs in special kind of a compounds which we call as aryl ether or allyl ether. Aryl ether or aryl ether. But now before going to the reaction, we must see what we call as allyl and what species we call as a allyl. So we'll go one by one. So here this position is known as the aryl one. For the time being we can call it as a phenyl because phenyl ring is there, but if another aromatic substituents or another aromatic rings would be there, then that group is known as the aryl one. You know the vinyl one, suppose X is here, I'll take it as a chlorine. So the compound is known as the vinyl chloride because your functional group is attached to a doubly bonded carbon, which is a sp2 carbon. So this is known as the vinyl, and a very famous plastic which is known as the PVC is nothing but the polymer of this kind of a compound, polyvinyl chloride. None of our business, let's move forward. And you might have seen such a type of compounds, where your functional group is attached to a sp3 carbon which is just next to the doubly bonded sp2 carbon. So this compound is known as the allyl chloride, and this kind of a group, if you're having this kind of a group, it is known as the allyl group. So now we are clear with allyl, vinyl, it's a vinyl one, sorry, and it's aryl, in this case it's vinyl, and it's going. So let's clear one thing more. Many guys gets confused between benzyl chloride and chlorobenzene. They think benzyl chloride and chlorobenzene is the same one, but not, guys. Chlorobenzene, you know, this is a chlorobenzene and this is a benzyl chloride, because this kind of a group where CH2 is the extra CH2 is present on your benzene ring, or you may say the sp3CH2, which is just next to the aromatic carbon, is known as the benzylic position. Okay, so here we are clear up to allyl, vinyl, phenyl and benzyl, all the things. Now what kind of a substrate we are going to need for this reaction? So you can see here you have a allyl one and here you have a aryl one. Basically this kind of a compound on heat undergoes 3-3 sigmatropic shift, sigmatropic rearrangement also known as, to give you something like this OH. Now just looking at the product, one might be saying you have to pick up this group and just join it at the ortho position of the benzene ring. But guys, if you number 1, 2 and 3, in case 1, 2 and 3, in the product you are getting the reverse sequence of your allyl group. Why it is so, we'll see in the mechanism. So let's go for the mechanism. In mechanism, so here you have the system of 3 and 3, 1 2 3 and 1 2 3, and the new bond is getting formed in the carbon, third and third carbon, hence the reaction is known as 3-3 sigmatropic shift rearrangement. I'll make a special video for the sigmatropic shifts and sigmatropic rearrangement later, but for the time being just we'll go with this reaction. In presence of heat, the bond opens here on the third carbon. That means this 3 and this 3 is going to form a new bond, and the rest of bonds gets rearranged. It's just a fact of shifting of the bonds shifting of pi bonds in a conjugated manner. So you are getting, see, these bonds are unaffected. We'll keep them as they were, sorry. Yeah, here we have oxygen, and you're coming, the third carbon is coming here. So this one carbon, yeah, here the second one is the new double bond is being formed in the number 1 and 2. So here goes 1 2 3. So as I told you, the positions of, or the sequence of allyl group is reversed in your product. Now if you go from your starting to product, starting is aromatic, product is non-aromatic in this case, but just to retain the aromaticity, this hydrogen goes off in the in form of H plus, which is then later occupied by this oxygen and becomes OH. Okay, so you are getting OH and this. This step is also known as the re-aromatization. And the stability of your product is nothing but the driving force for this reaction to occur. So I hope the mechanism is very much clear to you. In this step, there is one more possibility, that now see, you can see here you have 1 2 3 3 carbon system, and here is again 1 2 3 carbon system. There is another possibility of 3 3 sigmatropic shift rearrangement occurring between allyl and allyl groups. Yeah, allyl and allyl carbons, which is known as the co-rearrangement, and that's nothing but the topic of our next video. So we'll cover the co-rearrangement in our next video, but for time being, I'll just make you aware of the another product which is being formed here. So OH, and here is the car system of 3 carbons. But one thing is to remember, guys, in this case you're getting the sequence of external allyl group in this manner, but in this case you're getting again as your starting one. That means in ortho position, if your allyl group gets attached to the ortho position, the sequence of allyl carbons, or the sequence of allyl group carbons reverse, but in the para position they retains. Why they retains? Because at the first step they are reversed, and in second rearrangement, which goes like these and these and these again, the same arrows, I'll just show it with the dotted arrows. Okay, so it goes here and it goes here. Now you can see this one is again coming to this position as it is here. So this is what about the mechanism. Okay, now we'll get one more problem, and here is the problem. If I'll be having, here is CH3, here I have O allyl, and here is one more CH3, and it is heat. Okay, so guys, see, okay, so I have just shifted the double bonds, no problem. I'll go from this case. So I have 1 2 and 3, I have 1 2 and 3. The structure is very much symmetrical in case of just ring, so it doesn't matter whether this carbon attacks or this carbon attacks. And if this carbon will attack, then you are going in such a manner. Okay, so finally what you are getting is, here is CH3 unaffected, here is one more CH3, you are getting another allylic group, here is CH2, let's say, sorry, here is the double bond and O. Okay, like in the previous case, you had one hydrogen which would go as H plus, and then the ring would be rearomatized to give you a stabilized product. In this case, you don't have any hydrogen, you don't see. So as we see in the para case, it occurs here. So now your second step rearrangement is occurring here, and you will be getting a para product as a stable product. Okay, so it's again O double bond double bond. Now to rearomatize, you have one proton which will go inside and will make oxygen double bond to open, and you are getting the para substituted phenol. I mean, there are two ortho substitutions also, but your allylic group comes to the para position, and this becomes the major product. Major means obviously because there is no any possibility to replace the CH3. And what if all the positions are blocked? So this is the case if both of the ortho positions of your phenol or of your oxygen are blocked, then you will get a para position, and obviously as we see here, the numbering would be in this case, in this manner. Yeah. Now what will happen if you will have O, O, and again CH3 at the para position also. If you will go for its mechanism at any of the stage, whether this ortho, this para, or this ortho, you don't have any extra hydrogen which would go as a H plus and then re-aromatize your ring. That means, let's say if I'll form a intermediate, so it would be like, yeah, here is your O double bond, and here you will have, okay, in this case, if this allylic group moves through over the ring, there is not even a 1% chance of re-aromatization. That means your starting is more stable than your product, and hence the reaction doesn't occur because of the stability of your aromatic ring. Okay, so this was about aromatics. Now we'll see something from aliphatic. Okay, if this compound is heated, remember it's intramolecular reaction. So 1 2 3, 1 2 3. Again you have 3 type of system, and it can go right. Fine. So what you are getting is double bond O. Here is double bond. Okay. So here's your 1 2, and here's your 3. 3 and 3 is getting attached, and then you are getting this kind of thing. Fine. Okay, so this is what the product. Now in the case of your aromatic rings, the position where your third carbon comes, you will see the hydrogen has to go on. If the position where your third carbon is attached, that means here, if your hydrogen will go, and if it makes such a bond, let's say double bond OH. So guys, what is the product? What is this product we call as? This is what a enol. And you all know the enols and ketones are always in a dynamic equilibrium where keto form is more stable, hence this would be the major product, and reaction will not go further in removal of hydrogen. Okay, so guys, this was for this video, and yeah, as I told you, in next video I'll be covering up coke rearrangement. I hope you like this video, and thanks for watching. Just enjoy your chemistry and stay tuned.